Hello students. In last video, we saw second order differential equation of charge for series LCR AC circuit. In this video, we have second question of assignment 7.2. The question is derive expression for complex current for series LCR AC circuit. How do we know how much is the current passing through an AC circuit if inductor, capacitor and resistor are connected in series? We know that R, that is resistor, is an ohmic component, but the inductor and capacitor are not ohmic component. They offer reactance to the current, and then we don't know what is the actual nature of current, and then if we want to find out how much is the current at given time, we must have some expression of current for such circuit. So that is the topic for the video. Let us try. So first we consider a circuit in which we have resistor, capacitor and an inductor connected in this fashion, means they are in series, and this series combination is connected to an alternating source of voltage. Let the voltage be V. So I should be able to write V to be equal to VR plus VC plus VL. How come? Because whatever is the voltage across R and C and L, if we sum up these three voltage, it has to be equal to the voltage supplied by the source according to Kirchhoff's second law. Now we know that if the current here is I, then V can be written as VR can be written as I into R plus voltage across capacitor is obviously Q by C, where Q is charge uh, stored on the capacitor, and for inductor we know it is L di by dt. Okay, in last video also we had this equation. Now, as we don't know the nature of the voltage and current, what we can do is we will express V and I as complex numbers. So instead of writing V as Vm cos omega t or sin omega t, I will consider V to be Vm e raised to j omega t. I hope you remember that whenever we take z to be equal to z mod z e raised to j delta, what we mean is mod z cos delta as real part and mod z sin delta as imaginary part of z. So with the assumption that you remember this, we are going ahead. And if voltage is expressed as complex voltage, current should also be expressed in terms of complex voltage. Sorry, complex current. So we'll express I as I m e raised to j omega t. So let me label this as equation 1, equation 2 and equation 3. Okay, so now we know that if I is I m e raised to j omega t, di by dt, that is the differentiation of this equation I m e raised to j omega t, will give me I m j omega e raised to j omega t. Why I am doing this? Because I'll need it in equation 1. Equation 1 is having di by dt in it. So I am trying to find out di by dt, and I'll also try to find out q value so that I can substitute all the values in equation 1 and I can simplify it to get current. How did I get equation 4? Let me explain. If you are differentiating e raised to x with respect to dx, what you get is e raised to x. But if you are differentiating e raised to kx with respect to x, then you will get e raised to kx. Math student must be knowing this. Similarly, if you are integrating e raised to x with respect to dx, integration is e raised to x only. But if you have e raised to kx to be integrated by dx, the integration is e raised to kx upon k. Okay, so keep these equations in mind. It will help you understanding some of the derivative steps. Now, as I am going to need q also, let me find out q value. We know that Q is integration I dt, because I is dq by dt, and hence dq is I dt. Integrating both sides, integration dq is equal to integration I dt. So q is equal to integration I dt, we can write. So if I integrate, if I substitute I value, it is integration I m e raised to j omega t dt. I m being constant can be taken outside, and integration of j omega t e raised to j omega t will give me I m e raised to j omega t by j omega. Let me call it equation 5. Now, what if I substitute 2, 3, 4, and 5 in this equation? Let us see what we get. So left side becomes v is equal, sorry, left side becomes vm e raised to j omega t. First term on right side is r I m e raised to j omega t. What did I do? Instead of this I have substituted I m e raised to j omega t. Okay. Then second term q by c is now, if I use equation 5, can be written as 1 by j omega c I m e raised to j omega c, sorry, j omega t. And lastly, instead of this di by dt, we can substitute this, and then what we have is j omega l I m e raised to j omega t. Now, on left side we have e raised to j omega t, and on the right side in every term we have e raised to j omega t. So if we take e raised to j omega t common from right side, it will be cancelled out, and then what we are left with is Vm. Im is also common in left side, so we have r plus j omega l plus 1 by j omega c. And let me give it number 6. So now if I use 6 in equation 3, what we'll get? No, let me still simplify it. Let me make I am subject of formula. So I am, that is maximum value of current, is maximum value of voltage Vm upon R plus j omega L plus 1 by j omega c. Now, conventionally, imaginary part is not kept in denominator, and so if I have 1 by j omega c, ideally I should remove imaginary part from denominator. So what I do is I'll multiply it with j by j. So in numerator I have j, in denominator I'll have j square omega c. Now what is j square? It is minus 1, so it becomes minus j by omega c. Remember, in complex number, actually I indicates imaginary part, but in physics we use I for current, and hence for imaginary part we use symbol J. So in denominator of expression for I m, instead of 1 by j omega c, we will consider minus j by omega c. What is the advantage? Advantage is we can take j out. So Vm R plus j. Now I have omega L, and here I will take minus 1 by omega c. So the denominator is actually impedance. It can be labeled as Z. You have real part, you have imaginary part. Okay, so you can also write it as R plus J XL minus XC. Okay, so here is our equation 6, and let me call it equation 7. And then if I use equation 6 in equation 3, I can write equation I as Vm by R plus J omega L minus 1 by omega C into e raised to j omega t, or else it can be written as Vm e raised to j omega t upon z, or else you can write it as I is equal to V by Z. So this is the equation of complex current in case of AC circuit with series combination of LCR. You can write it as I is equal to Vm e raised to j omega t by mod Z e raised to j delta. So Vm by mod Z e raised to j omega t minus delta. Okay, this is also one way of expressing it. And then if you are asked what is delta, what is mod Z, you can say that if we plot this Z on a complex plane, we'll get mod Z as well as delta. So let me plot that also. So if this is the real axis, this is imaginary axis, then I can take real part here, resistance, imaginary part here, XL minus XC, and then this is mod Z. Okay, so I can say that mod Z is under root of R square plus XL minus XC. Okay, and what is delta? Delta is this angle. And how do I get delta? So tan of delta is XL minus XC by R. So that is how we can express mod Z and delta both. And then if I replace this part as Im, then I can write that I is equal to Im e raised to j omega t minus delta. So real part of current is Im cos omega t minus delta, and imaginary part of current is Im sin omega t minus delta. So that is all about equation of complex current. Most of the time what we need is this. So we'll consider this as equation of complex current. Imaginary part is not used anywhere. So for the coming topic we will consider equation of Z. Don't forget this equation. Equation of V. Okay, we will consider equation of V as Vm e raised to j omega t. We will consider equation of Z and equation of I for the forthcoming topic. This is all for this question. Thank you.